So I'm now going to introduce our first speaker, so Dr. Catherine Breslin, who heads Amazon Alexa over at Cambridge. And so she's got a PhD in linguistics and automated speech recognition and heads the Alexa unit to scale Alexa products around the world. So without further ado, I want to introduce Catherine onto the stage to talk about scaling Alexa. Thank you.
Hi, my name's Catherine Breslin. I lead the Alexa machine learning team in Cambridge, here in the UK. So I hope that some of you have heard of Alexa. Alexa is the cloud-based service which powers devices like Amazon Echo and the Fire TV. You can use your voice to control Alexa. If you have a device like the Amazon Echo, this is something about how Amazon Echo works behind the scenes. So you begin by saying the wake word, Alexa. The device registers that and wakes up. You see the blue ring on top light up, and then Alexa starts streaming audio up to the cloud. Once that audio is streamed up to the cloud and you're asking Alexa what you want, in this case, play Message in a Bottle by Sting. So that audio gets up to the cloud and hits the Alexa voice services. Alexa voice services first runs automatic speech recognition, or ASR. That's the module which converts that audio into text, which is the best guess at what we think that user has asked for. The next thing we do after that is to run natural language understanding. And this is to understand the intent of what the user's asked for. So in this case, they've asked for some music, but equally, they might have asked for the weather forecast or to ask a factual question. So once we've understood the intent of what the user's asked for, that intent is dispatched to the relevant skill. Now, a skill is a service which handles each intent. That skill takes some action and decides how to answer. In this case, the device has to play music, so the play directive is sent back to the device, and that audio is loaded from the user's personal library and played. In other cases, if you've asked for a question or you've asked for the weather forecast or something else that requires a response, Alexa can speak back to you. So this is a pipeline of many different machine learning technologies, voice and language technologies that work together. So we begin with the wake word detection on the device, the speech recognition, the language understanding. There's machine learning in some of these skills, some of the more complex ones like music recommendations or question answering. Natural language generation and speech synthesis all work together. Now, Alexa launched in 2014, November 2014 in the US. And since then, we've added more features. We've enabled Alexa on more devices. And we've also, which has been one of our harder challenges, allowed Alexa to work in new languages. So we launched in German, we launched in Japanese, and this week we're actually shipping in France for the first time. So voice is a really easy and convenient way to interact with devices. It's very natural to talk to a machine. But this pipeline is only made possible because we can scale these technologies across different languages. So I'm going to talk through some of the ways that we have scaled up Alexa across languages. And I think there are three main things that have contributed to this. The first thing we take advantage of is data. The second is computation. And the third is algorithms. So I'm going to talk through how we use these. So data is obviously the key thing for any machine learning system. Without good data, you cannot build a good system. And Alexa is no different. And we need data which matches to the task which we're using. When you're serving models to customers, the data which they're trained on should really mimic how those customers are going to use that device. Now, it's not enough just to have the raw data of how users interact with Alexa. What we typically need is that data to be labeled. For speech recognition, for example, we need audio which has been transcribed. For natural language understanding, we need text which has been annotated with the intent of what the user is asking for. And this data annotation process can be very time-consuming and expensive. So sometimes we have to be a bit more creative about how we create our data for Alexa. So there's a couple things we've tried here. One thing we've done is we've built our own Alexa skill. This is called Clio. Clio is a skill which you can use to teach Alexa your native language. It's available on all Alexa devices, so you can enable it and talk to Alexa in your own language. And this means that you can teach Alexa, and we can learn how people ask for things in different languages. A second thing we've done to get data across multiple languages is to use machine translation. Now, machine translation itself is a machine learning task which needs data to be trained on, but there are very good off-the-shelf machine translation systems. And we've used these to take our data in English and translate it into other languages in order to bootstrap those models. Now, it's not as straightforward as just taking data and translating it, because there are some quirks that we have to consider. For example, if I was to say, play the Yellow Submarine in English, and I translate that into German, I'm going to translate the song title. But actually, the German user is more likely to ask for the original English song title. So we have to be a little careful about how we use machine translation. There are other things like the songs that are popular in German and not necessarily the songs that are popular in our English data. But if we can get around these, then machine translation can be a good way to bootstrap languages like German. There are some languages where machine translation doesn't work as well. For example, English to Japanese is a much harder translation task than English to German. And so typically we find that with languages that are closer to English, we get much better results. But machine translation has proven effective in helping us to bootstrap internationally. Of course, once you've got data, you need to be able to process that data. And here, I think it will come as no surprise that we use AWS. And we use AWS's elastic computing capability to enable us to scale up and scale down our computing as we need. So we think very carefully about how we parallelize and how we build our clusters of machines, which are going to enable us to do the training and testing for the models that we're building. Now, there are some parts of the model training process which we can parallelize very easily, something like data pre-processing. We can just spread the data across multiple machines, do the processing, and combine the results together at the end. But there are some things which don't parallelize quite so well. And one example is neural network training. If we parallelize our neural network training across multiple machines, now instead of being able to work independently, those machines have to talk to each other during the training process. But if we can be smart about how and when we do those synchronizations between those machines, we can get very nice speed-ups in training. In one paper which we published when we benchmarked this, admittedly it was from 2015, so it's a little outdated now, we found that if we scaled up to using 80 GPUs to do our acoustic model training, acoustic model is the part of the speech recognition system which handles audio. If we use 80 GPUs for this, we could get a throughput of almost 4 hours of audio every second, which when you're training speech recognition systems on large amounts of data, means that you can iterate much more quickly on your model training and get models out faster. So the third thing that we've leveraged in order to scale Alexa across languages is the algorithms we use. Now, when you're building models to serve to customers, you're not always concerned with state-of-the-art accuracy. Of course, you want your models to perform well, but there are other things that you have to think about as well. For example, we're especially concerned with latency. That's how quickly the models respond. When you're having an interaction with a voice system like Alexa, if Alexa takes a long time to respond, then actually that interaction can become very unnatural and people don't want to use Alexa. So latency is something that we were very concerned about, and making sure our models work in real time. A second thing we're concerned about is maintainability. So as we deploy a model, as soon as you've deployed a model, it can quickly become outdated, especially when you're working with systems that people are asking about current trending topics. The trending topics that happen change every week. For example, a new movie gets released with an obscure name, or some event in a part of the world that you've never really spoken about before. And people start asking about these. So as soon as we have deployed our models, they rapidly become outdated. So we have to worry about how we can build and maintain these models once we push them to production. So thinking about how we use algorithms to scale for different languages, we've made heavy use of something called transfer learning. It turns out that you can take a machine learning problem and build your model for a particular task. And then often, depending on what that model has learned, you can transfer some of what it's learned to another task. In our case, we can use transfer learning to take models that have been trained for English and then transfer some of that knowledge to German, for example. So if you think about speech recognition systems, our speech recognition system learns a lot of stuff about audio, which can be transferred between languages, no matter that those languages output different words eventually. And by being smart about how we use algorithms like this, we can achieve much better scale than we could if we built from scratch every time. We also want to give back to the research community. One way we've done this is with the Alexa Prize. Alexa Prize is a university competition which we ran to advance human-computer interaction. It's run amongst a number of university teams, and those teams are charged with building a social bot that can converse in an open-ended fashion with users. Now, that competition had its first year last year, and its second year has just got underway. It's a global competition and has 8 teams participating this year, one of which is from Heriot-Watt in Edinburgh. Another thing we've done is to release data sets. The data set we recently released is called FEVA, Fact Extraction and Verification. This was a collaboration between some of my colleagues in Cambridge and the University of Sheffield. The data set itself consists of a number of Wikipedia pages, facts which were derived from those Wikipedia pages, and annotations of those facts about whether they are true or false, or whether there is just not enough information in the Wikipedia pages to be able to verify that fact or not. The facts are things like Lorelei Gilmore's dad is named Michael, things which you can quite easily see from the Wikipedia pages or not. Data sets like this are expensive to build and maintain, but they have a great advantage when multiple teams across the world can benchmark on the same data, and they're a great way to drive innovation and progress. So I've talked a lot about how we have built and scaled Alexa. I just want to leave with a few words about where we're heading in the future. So I believe that in the future, these systems like Alexa will start to become more contextual. They'll know more about the world they operate in and how you want to use them. For example, if I ask my Fire TV to play Frozen, or I ask my Amazon Echo to play Frozen, on the first I probably expect to see the movie being played, and on the second I expect to hear the song. So this sort of context is something that I think systems will get much better at handling. I believe that systems will also become more customizable. So you will be able to use Alexa in ways that you want to, tell Alexa more of your preferences. And third, I think we'll hear more about this later, but I believe these systems will become much more conversational. There's a lot of interesting research directions right now in human-computer conversation, and I believe we'll start to see some of those come to systems right now. So voice is a really hard problem, building an end-to-end system that can do chatting with people. We've solved a lot of hard problems to get where we are today, but if you've used these systems, you'll probably realize that we still have a long way to go. So as we say at Amazon, it's still day one. Thank you for listening.